Okay, so when we were discussing in the last lecture, we were trying to see what is the swing limits or the maximum or the minimum swing that we were able to apply in this common source amplifier that I'm sure all of you are very familiar with. And we said that in this particular case, what is the maximum VI that I can apply, and that is determined by the fact that that is determined by the condition when this transistor actually goes into linear region. And for that, what we did, we said that total or VDS total should be greater than equal to VGS total minus threshold voltage. So what is VDS total? So this is quiescent plus the relationship between input and output, which is gain, AV times VI. This should be greater than quiescent, that is VGQ, minus plus the input in this case minus threshold voltage, and which essentially led us to the conclusion that this AV times VI was minus GMRL in this case. So VGQ minus VTH was overdrive, this VDQ minus GM times RL times VI. So VI has to be less than equal to, or in this case, VI max has to be less than equal to okay. So this algebra is fine, it checks out. But what the important takeaway from this is the fact that if you try to increase gain, you reduce the maximum amount of signal that you can handle at the input side. And that makes sense, because if you increase gain, which means the output will swing more. If the output swings more when the supply is limited, right, you cannot really go to VDD or really go to ground. So you have to operate between certain range. If the range is limited and the gain is high, the input has to be smaller, right? So it's basically saying the same thing in a different manner. Okay, so now some of you could have asked me the question that why did I say that the total voltage is this at the output? The total voltage is actually not this, right? I can say the total voltage is quiescent plus the change in current times RL, right? So change in current is what? I mean, my total current is how much? The total current, if I say this I total, what did I conclude here? I said the I total is IDQ plus GM times VI. This is what I said the I total to be. But actually my I total is what? I total is mu Cox W over L 1 over 2 VGQ plus VI minus threshold voltage whole square. Right? So that is my I total. So under what condition is this I total, this actual I total and this small signal I total same? Right. So yeah. So as he's pointing out, so I can break this entire stuff as if I take this VGQ minus VTH terms together, so I get one IDQ term. Then I will get mu Cox W over L VGQ minus VTH times Vi, and then I will get another term of half mu Cox W over L Vi squared. Okay, and what is this? This is GM. And what is this stuff? This is the term that is giving me distortion, right? So this will give you higher harmonics. And I mean, in the initial assignments that you did, you saw that if we can limit the swing, if you can limit Vi to less than whatever the requirement might be, then I can neglect this extra term, right? So that's what we are going to do. We are going to say that we essentially are trying to design a linear amplifier. I mean, it's a nonlinear element, but we want to linearize the amplifier and operate under a condition where the linearity of the signal doesn't get compromised, which essentially means that by definition of that, I am making the commitment that the Vi will be such that the higher order terms can be neglected. As a designer, I'm making that commitment, which means that for our analysis, I can neglect this higher order term and I can limit my total as the quiescent plus linear incremental. So quiescent plus small signal to be the total input current, total output current, which essentially means that now if I have to find out the voltage at some node, I can simply say that I'll neglect whatever the higher order terms are. I will simply go by the linear analysis, and total at any point is equal to quiescent at that point plus incremental at that point, right? So that point might be a voltage, or that point might be a current that is coming into the node or going out of the node. So remember this, total is equal to quiescent plus incremental, where incremental is the small signal linear equivalent. Okay, so we'll be using this everywhere. So the reason I spent 1 minute on this is because now if I ask you, this gives me the upper swing limit, right? How far I can go. The previous analysis, what is the maximum voltage to which the gate can rise before my transistor goes out of saturation. So now if I ask you, what will be the minimum, right? So this is Vp sine omega naught t. This is VGQ. So what is the minimum that Vp can go before it becomes acceptable for, I mean, it's within acceptable range of operation? Okay, so it's one answer was VGQ plus small signal. In this case, Vp is going down, so VGQ minus Vp should be greater than equal to threshold voltage. Okay, so why do you say this? I presume it's because the transistor gets, I mean, it's completely cut off. Now, while this is mathematically true, there is a caveat if we use this constraint. And the caveat will become clear if I just say that instead of putting this MOSFET, I use a BJT, for example. BJT is also a source. I can also model a BJT as a voltage control source or a current control source, doesn't matter. But if we ignore the base current, it's more or less a voltage control current source. So now the relationship between I to V in a BJT is, do you recall? No, total. Let's say I have input, let's say I have VBE. Let's say this is VI. Okay. What is the relationship between VI and total current? Exponential, right? So e power VI by KT over Q and so on, right? So now if I use the same argument as we did to realize, to put my current to 0, what is the value of VI that I need to go to? Yeah, and if I just, it should be very, very small than BT. And if I just use the total expression, then, I mean, you can say that VI has to go to absolutely 0. Okay.
But obviously, we understand that if Vi goes to absolutely zero, it's definitely not usable, but it ceases to become usable even we go to absolute zero, right? Because you don't see the device suddenly doesn't stop to work when you go to zero, right? It starts to degrade much before you go to zero. Similarly, in case of MOSFET also, it's not as if that when you go to VGS equal to VT8, suddenly the device is not working. It stops working reliably much before you go to absolute zero. So that is why we will not use this constraint. The constraint that we will be using is again the same thing that we talked about 2 minutes back, and we'll essentially say that your device, the lower limit of the input voltage is determined when total current, total output current, or total drain current goes to zero. And what total drain current by the definitions that we have been following? It's IDQ plus incremental drain current, incremental linear drain current, and that is GM times VI. This goes to zero. Okay, so which means that VI has to be less than, mod of VI has to be less than mod of IDQ by GM. Okay, so this is the constraint for a common source amplifier. This constraint will be different for different cases, but what you need to understand is the fact that the constraint that we'll be using in both cases, the going maximum swing, maximum allowable swing at the output or the input, and the minimum allowable swing is determined by quiescent plus incremental small signal. Do not try to set the total current to zero by using VGS minus VT whole square. Okay. Any questions? Okay, so let's spend some more time on this. So when we plot ID versus VG for our MOSFET, we essentially say that using the current equations that we are familiar with, ID is 0 till VTH. And if everything is in saturation, it goes like this. Okay. And then we say that we'll probably have a bias point somewhere over here. Okay. And we select a bias point VGQ, IDQ, and then say that our signal will swing around this bias point by some margin. And how far can I go on right or left of that so-called bias point is determined by how linear is this curve. Okay, so if the curve is very linear, I can go quite a lot left and right as far as the input is concerned, but the curve is very non-linear, I cannot do that. Okay, so now when you say that I will set the total current to zero, what you are essentially telling us is that I am saying it is okay for us to swing from here to here. Okay, the input can swing from VGQ to VTH, but even by eyeballing this curve, you can figure out that it's significantly nonlinear, right? Because this is not a straight line. Okay, so by making this approximation, by invoking this condition of I will set ID to be equal to zero, inherently you are inviting a lot of distortion into your signal. Okay, so on the other hand, what are you saying? What I am saying is, instead of setting this total absolute current to zero, I will set the quiescent current plus incremental current to zero, incremental linear current to zero. So what is incremental linear current here? From this slope, how can you figure out what is the incremental linear current? Draw a tangent, right? GM is basically the tangent to this curve. So you draw a tangent
and then say that IDQ plus the extrapolation of this tangent goes to 0, right? So this is IDQ plus GMVI goes to 0, means quiescent plus extrapolation of the tangent is going to 0, which means I am limiting my swing within this region. That inherently is much more linear than your total current going to 0, because the swing that I am limiting it, the allowable swing that I am limiting my output to go, the allowable swing that I am limiting my device to operate in is lesser than what it would have experienced if I would have allowed the total current to go to 0, total absolute current to go to 0. Does that make sense?
Sir, so on the first equation,
yes.
even basically transistor might go from saturation region to linear region as well.
Which equation?
The earlier equation, like
you mean the
this equation, VGS minus VP is greater than VTH. When VGS minus VT is equals to VTH, in that case, transistor may can transistor come to the linear region, sir? What I was thinking, like this equation basically saying that the transistor may go from the saturation region to linear region, but from this equation IDQ plus GMVI.
No. Okay. Why do you say it can go into linear region? That is what I'm slightly confused with.
So, sir, the effective gate voltage, that
right.
VGQ minus VP, the
right.
effective voltage that
correct.
is equals to the threshold voltage.
Right.
It is just on.
Just on. Yeah.
Just on. So can it be, sir? It might be the transistor might be in the off condition.
Yeah, I mean barely on. Fine. Okay.
But sir, in the second equation, the IDQ plus GMVI, this equation basically saying that the transistor is always on, but we are also in the saturation region because there is a linear approximation.
Correct. Yes.
So we are not going into the triode region.
Yeah, we are not. And can you go? I mean, are we running the risk of going into triode region if we use this equation? Is that the question?
From the first question, can you
from here?
This question.
From here, how will you go into triode region? I mean, you are. What is this constant? This constant is saying that how low can this gate go? When the gate goes low, are you going towards the triode or away from triode? When gate goes low, drain goes high, right? So you are going away from triode.
But it could go into the cutoff region.
Yeah. So if you, that's what it is going towards the cutoff. Now, the whole purpose of this discussion is to establish when do I say that it has gone sufficiently towards cutoff, and that is the limit that I am going to use. Is it when transistor fully actually shuts off or before that? Because if you wait for the transistor to fully actually shut off, then signal is already pretty much distorted and it's unusable. Right? So I haven't derived what is that total harmonic distortion when things go in that domain. That is not a part of this course, but it's easy to appreciate the fact that if you are very close to cutoff, you will have a lot of distortion. I mean, even the sine wave will probably not look like a sine wave, right? So you don't want to go there.
But that thing is not appearing from this equation.
That here, this equation is based on the fact that, so what is this based on? This is based on the fact that we have linearized our operation, right? So if we are okay with using small signal model, which means I am saying that around the range of small signal swing, I can ignore the higher order terms, which means I can say that till the time, till the range in which the small signal model holds, I am fine. And the approximation that we are making is the small signal model is holding till IDQ plus incremental is 0, right? So by the way, since we are on this topic, what is this point? Yeah, I mean, so instead of going there, we can go step by step. But I mean, essentially, you set this to 0. When you set this to 0, what do you get this point to be? How much is this difference if you set that to 0? So when I say IDQ
plus GMVI. What I am saying, IDQ plus maximum GM times maximum input, right? So let's say I call it VP. This I am setting to 0, which means how far can VP go from quiescent point? So we were around quiescent point here, and how far can I go? This is IDQ by GM, right? Once you move your VP, once you move your quiescent, once you apply a signal which is equal to IDQ by GM, a sinusoid which has amplitude of IDQ by GM, then your total current plus incremental current, small signal incremental current goes to 0. And as it turns out, this is equal to, if you put in the values, this is equal to what? Mu Cox V overdrive squared by mu Cox V overdrive, right? So this is half of V overdrive. V overdrive is VGS minus VT, right? So essentially, if this was your quiescent V overdrive, so this was your V overdrive quiescent, and how much you can go from your quiescent till you honor linearity, it's half of that value. So essentially, a cheat code for this is if you assume you bias your transistor with a VGS minus VT of 200 millivolt, you can probably apply an input of 100 millivolt, that is between the gate and the source directly, and still say that, okay, it's probably still in sufficiently linear region, sufficiently in the linear region of operation, not the triad region, right? It's the linearity is holding. Okay. Any questions? If it goes into linear region, then it's a problem. So you have to honor both, right? So for essentially for any transistor that you see, you have to figure out two conditions: whether what is the maximum input that you can apply before it goes into triode, and what is the minimum input that you can apply before it goes into cutoff, right? Incrementally cutoff. And if it's a sinusoid that you are applying, then obviously whichever gives you the worst case condition determines the amplitude of the sinusoid. Okay, so that's what you have to do for all transistors that you see. I mean, let's do an example. Let's do an example that will help make things clear. So let's say VDD is 3 volt, RL is 1K, mu Cox W over L is 2 milliamp per volt squared. Okay. Okay, so let's say a circuit is hooked up like this. Mu Cox and W by L are identical for the two transistors. And this VGQ is 2 volt and threshold voltage is 1 volt. Okay, so now help me through the process of figuring out what is the maximum VP that I can apply before both the transistors. I mean, you would want both the transistors to always remain in safe operating zones, right? Before any one of them goes out of safe operating zone, that is saturation, right? So what should we, how should we approach this? You tell me how should we approach this, I'll do the maths on your behalf. Pardon? I can't hear you. PDS of the first MOSFET. Okay, but yeah, so basically what we are saying is that you have to first find out the quiescent point, right? If we don't have the quiescent point, there's no point doing this. So find out the quiescent point. What will be V1?
What is the current? Current is 1 milliamps, right? Current is 1 milliamps, and you have a drop of 1 volt across RL, because 1 milliamp times 1 k is 1 volt. So V1 is 2 volt. So this is 2 volt. Okay. So if this is 2 volt, this I know that, I mean, M1 and M2 are identical. Both of them seems to have the same VGS. So this output will also be 2 volt. Okay. So now also we know that current is ID2 is 1 milliamp. So ID1 is 1 milliamp. Okay, fine. So the quiescent points are set up. What is the next step? What GM? Okay, what is GM? We need to figure out the values of the quiescent, I mean, incremental models also, right? That's correct. So what is GM? Use any of the favorite formulas that you want. Mu Cox W over L V over drive, which is 2 millisiemens. Okay, fine. We have quiescent, we have GM. Now what? So first you have to see what we, I mean, are you talking about you are increasing input, decreasing input? Which condition are you trying to figure out, right? Okay, but anyhow, you had increasing input. Okay, so we are increasing input. So when I'm increasing input, what is likely to happen? This node is going to decrease and this node is going to increase. Okay, so when you are increasing the input, which transistor is trying to go into linear and which transistor is trying to go into cutoff? First is trying to get into linear and the second is trying to go into cutoff, right? So now then your job becomes to figure out which one is going faster, because the one that is going faster towards its out, I mean, towards out of saturation rather, is the one that will set your maximum swing. Okay, so in order to figure that out, what will you do? What is the next thing that you need to do? Yeah, right. His VGS is decreasing.
But VGS is increasing.
Yeah, fine. So yes, VGS is increasing.
But when VGS is less than VGS, that time it will go to cutoff.
Yeah, so if it starts off with being in saturation and it's going then away from saturation, right? I mean, going more deeper into saturation, isn't it? So his question is, how do we figure that M2 is going towards cutoff or towards triode, right? So to start off, was it in saturation region? It was in saturation region, right? Because its VDS is 2 volt, VGS is 2 volt, threshold voltage 1 volt. So clearly it is in saturation. Now when input goes low, which means VGS is decreasing, but VDS is increasing. So it's going more into saturation, right? So we need not bother about that end. We have to now be concerned about the lower end. That is it going more closer to closer to cutoff? Okay. Okay, fine. So now we figured out all the necessary parameters, but then what is the critical step? What should I now do to figure out the actual limits?
So the input is increasing, so
right.
To find how much output is decreasing.
Right. So how much is it? So if okay, so see, I mean, what have we done all till now? We have said quiescent plus incremental. Quiescent plus incremental current, quiescent plus incremental voltage. So which means you have to find out incremental voltage. So when I say incremental voltage, what does it mean? When I say what is the incremental voltage at the output, given that you know the voltage at the input, what am I referring to? What am I trying to get? Gain, right? So what is the gain between this node, input and output of M1? Which is equal to how much? GM times RL is 2. So I can say that my total output is
2 volt minus 2 gain times VI. Right? And what is the total current? Total initial current was 1 milliamps plus 2 millisiemens times VI. Let me write it in GM terms only. So similarly, now I turn my attention to M2. So what is the total current now? Yeah, VI. I mean, now depending upon whether VI is positive or negative, I'll replace, right? VI is essentially a dummy variable, right? Okay, so the total current ID for M2 is 1 milliamp. Then what in terms of VI?
GM times 2 VI.
Right. So minus GM times 2 VI. And why 2 VI? Because this node is incrementally swinging by 2 VI. If that node is incrementally swinging by 2 VI, total current at the output will be 1 milliamps minus minus the swing times GM. And the swing is 2 VI. So twice 2 GM times VI. So what will be the total output voltage now? How much is the gain now? Gain between between the input of M2 to the output of M2 is 2, but between VI to output of M2 is how much? 4, right? So this is plus or minus. So now all your necessary equations are set, all necessary conditions are set up. You know incrementally each node and each current, how is it going up and down. So now your job is to just see whether which one goes out of our operating condition first. Okay. So now tell me, if I have to consider, obviously then you have to do one by one, each transistor at a time, and then you figure out what the final answer is. So in this case, if I start with M1, what is the condition for maximum swing before M1 goes into triode? So M1 so this condition is M1 to triode. Okay, walk me through the maths. Okay, so let me write out the total, right? So total is VDS should be greater than equal to VGS minus VT. So total VDS is how much? 2 minus 2 VI should be greater than 2 plus VI minus 1. Is that correct? 2 minus 2. Okay, fine. So which means 3 VI should be less than 1. Correct? So VI has to be less than 1 by 3 volt, right? So M1 going to triode. So VP condition, that the condition that I'm getting on VP max is equal to 1 by 3 volt. Okay. So now let's do the other one. M1 going into cutoff. This should be easy, or rather straightforward. What will be the condition on VP? No, not VGS minus VT, right? Total incremental plus quiescent is 0, which means you have to set this to 0. right? So the lower limit is set by current going to 0, not the absolute current, so quiescent current plus incremental current. That's the definition of absolute in this sense. So obviously this becomes 1 milliamps by GM, and that is half, right? GM is 2 millisiemens, so VP max is 1 milli by GM, which is, or rather let me say VP min, 1 by 2 volt. So, so if we have to, if M2 was not there, then what would be the maximum amplitude of sinusoid that you could have applied under whatever bias conditions that we have set up? 1 by 3 or 1 by 2? So what I'm saying is allowable sinusoid is 1 by 2 sine omega naught t or 1 by 3 sine omega naught t. Pardon? 1 by 3, right? Because obviously if you satisfy 1 by 3, if you satisfy the triode case, you're automatically satisfying the cutoff case. Okay, so yes. Which point?
Like for the cutoff also we can apply the VGS. I mean the total gate voltage is less than VGH.
Yeah. So you can, but I mean that's what I referred to here, right? So when you are saying total gate voltage is less than VTH, then what are you saying? You are saying that it's okay for me to deviate from quiescent point all the way to here, right? So when you deviate so much, you become essentially incur a lot of distortion. You can no longer ignore these terms then. Cannot no longer ignore these VI squared terms. This is also simplistic, right? You will have other terms also in a realistic transistor. Okay, so if you cannot ignore that, which means its transistor is already into a lot of distortion, which means it's unusable, right? So, I mean, why use a condition under which my transistor will become unusable?
What is the voltage at the gate for this applying this condition? When the distortion kind of things.
Yeah, you tell me.
So it will be like 2 volt minus VP, that is equals to threshold voltage, right? 2 volts minus 2 volt minus VP.
So what? So that is the effective voltage.
Okay.
Correct.
So that is equals to VTH or less than VTH, then it is cut off.
Correct, but we are not going there.
But sir, just I have to see what's the value of.
Okay. So yeah, why don't you calculate that? So what is the value of? So his point is, if I don't use this whatever we are using right now, and if you go by the absolute value, then what is the absolute value of current going to 0? Then what is the maximum VP you are getting? Is that the question? So find out what is it.
1 volt.
It is 1 volt, right? But with this constraint, we are getting half a volt. So this is much more of a tighter constraint. Makes sense, right? Because you are not waiting for the absolute current to go to 0.
One question, sir, like when this current is becoming 0, still the gate voltage is there.
Right, yeah.
Current is 0, but the gate voltage is there.
There means you have incremental gate voltage. Yeah, and the transistor is still in saturation.
How's the current is getting 0, sir?
So it's an approximation, right? Current is going to 0 because we are essentially saying we will neglect this term and we'll say that the total current is this. If I take the squared term, then whatever you are saying will come into picture also. So that's the whole point, right? Correct. So for doing all our small signal analysis, if you are comfortable neglecting VI squared, we should use the same benchmark to establish our swing limits also. That's the whole point. Right? Yes. Yes. Yeah. Okay, so what I meant was, okay, so maybe I should do this. I mean, if I go by absolute value, then it should be minus, right? So you are setting this to 0. So then it should be minus 1 by 2, right? So the point here is You have a sinusoid. If I define this to be the maximum amplitude, Vp max, and this to be Vp min, then which one is higher in this case, right? In an ideal sinusoid, you have both. You want, in a sinusoid, Vp max is equal to Vp min, but let's say you get a condition where the condition that we are getting here is the maximum amount I can apply on the higher side is 1/3 volt or 0.33 volt, and then on the lower side it's 0.5 volt. Okay, so now what is the maximum amplitude of sinusoid that I can accommodate? Then clearly, without distortion, the amount of without acceptable distortion, the maximum sinusoid amplitude will be 0.3 volt, 33 volt, right? So that's the whole purpose of choosing the lower one. Okay, so this is as far as taking into consideration only M1 into account, but our circuit also has M2. Okay, so now do the same thing for M2. So what is the maximum Vi before M2 goes into cutoff? M2 cutoff. So which condition am I? Yeah, current is 0, right? So I know I have already in the first when we set up the total circuit, we had figured out what is the total incremental current and quiescent current. So this we have to set to 0. If we set this to 0, what do I get? Vi to be equal to Vp max has to be 1/2 gm. Is that correct? 1 milliamp by 2 gm. So which is how much? 1/4, right? 0.25 volt. Okay. And this clearly is lesser than the other two conditions that we got. So it looks like this takes the cake. What about M2 triode? Condition of M2 triode, what will it be? Total VDS should be, which is, so 2 plus, what was the condition? 2 plus 4 Vi should be greater than 2 minus 2 Vi minus threshold voltage, right? 2 minus 2 Vi minus 1 volt, which means 6 Vi should be greater than minus 1. Vi should be greater than, I mean, if I say mod, because we know which direction we are going, it's 1/6. Okay. So among all the conditions that we got, this is the one that is the minima. This is setting the bottleneck for your signal swing. Yes. What is the question? Right. Yeah, so you can assume it to be like that. It's not because 2 MOSFETs 2 GM. Why? How come you are getting this 2 GM? You are getting this 2 GM because if you have, let's say you have 1 milliamp of signal swing here, that will correspond to 2 milliamps. Sorry, 1 millivolt of signal swing at the input. That will correspond to 2 millivolt of signal swing at the output of M1, which will correspond to the total incremental current being GM times twice the swing, because the second transistor is seeing twice the swing. That's why you are getting the 2 GM, not because you have 2 transistors. It's not as if I have 3 transistors, I get 3 GM, right? Yeah. Right. Right. That is okay. So his question is, if I just I mean, we did the common source amplifier and it seems that the swing limit is VI by, ID by GM. So if I simply do ID by GM here, it looks like I'm getting more, right?
Then if we equate 2V minus 2VI equal to 0.5.
Okay.
We get something like 0.75.
No, right. I mean, so see, I mean, the idea is, so we are not, what we are not saying is, we are not trying to figure out what will be the condition if I use this in isolation. If you use only M2 in isolation and apply the VI at the gate of M2, then you will get a separate set of swing limits. But we are not doing that because this transistor is not seeing VI as a swing at the input. This transistor is seeing twice VI as a swing at the input, that is essentially, my next question would have been, why do you think the swing limits are being set by M2 and not by M1? Because it looks like, I mean, all the conditions for VI are worse when I calculate M2 than when I'm doing M1. So why is that? It's because M2 is seeing larger swing with respect to M1 at its input. Because there has been an amplification, the signal has gone through a stage of amplification before it has appeared at the gate of M2. Okay, so because the signal has gone through a stage of amplification, it makes sense that this M2 is deviating much more from its quiescent point, right? It makes sense that M2 is deviating much more from its quiescent point for the same input that was applied to the input of the network, right? Is that the question essentially that you are asking? Yeah. Right. So as it turns out, so this is one problem if you have many stages, many gain stages cascaded one after another. If you have many gain stages cascaded one after another, what ends up happening is that the final stage always sees a lot of distortion, because the input to this previous stage, input to the final stage will be swinging much more than the input to its previous stage, and so on and so forth. Okay. So that's why sometimes in many open loop design, even though you might want to cascade multiple stages, this distortion is something that you'll have to be careful about. Okay. Any questions before we break? Yes.
While designing amplifier, so this swing limits trial function will be there, or after designing the amplifier, again you have to decide this is my swing limit.
Yeah. So good question. His question is that, if you this is all the, I gave you quiescent point, I gave you everything and asked you to calculate swing limit. But when you are in charge of a design, then how do you approach, right? So then you'll have to, then it becomes a co-design, right? Nothing is given to you. So you start off with something. Maybe you start off with whichever parameter is most important to you. If gain is most important to you, set your transistor up for gain and then see whether whether you are getting sufficient swing limits. If it's not, then you go and tweak the design, right? So you can, you have to start somewhere, right? So you start with whatever suits you and then see what how the other parameters are being set up. Okay. Yeah, but that's essentially the story of a life of a designer, right? Where to start. Okay, fine. So we'll stop here. We can move to L7.